let's look at an application for having a linear system with several variables. So let's suppose that we build this circuit. So this sort of circuit diagram, these wiggly lines, these are resistors. These just resist the flow of electricity. The straight lines are just wires that hook everything up. And these symbols here, these are batteries. So here we have a 4-volt battery. Here we have a resistor that's 16 ohms. The unit for resistance is ohm. And here's, so the bottom side of this resistor is connected up to the bottom sides of these resistors. And here's another 5-volt battery. And the thing about this sort of circuit setup is it's kind of hard to know how much current is flowing through each of these resistors. That's something that if you're going to build a circuit, you should have some idea of how much current is flowing through your resistors, because if too much current flows through your resistors, it's going to start a fire. So we'd like to know how much current is going to flow through these resistors before we power the whole thing up. So the thing to know, there are two things to know about how circuits work. So the first is called Kirchhoff's law. I don't remember how to spell Kirchhoff's, so I'm not going to try. But what Kirchhoff's law says is that the sum of voltage drops around each loop in a circuit is 0. Okay, you can see we have a couple loops in our circuit. So if we go around one of these loops and account for all of the voltage drops as we pass circuit components, they should all add up to 0. And you can see that's going to give us an equation, because we're saying that some sum of things is equal to 0. The second thing we need to know about how circuits work is that when you go across a resistor, so the voltage drop across a resistor is, so it's a voltage drop, so V, and it turns out it's the current, which the symbol for current is I, which is confusing because you'd think it would start with C because current starts with C, but C is actually, there's another electrical circuit value that also starts with C, and that's the symbol that, that's the value that gets the variable C assigned to it. Anyway, so I is for current times R, and that's for resistance. So Kirchhoff's law, this first fact, is going to give us some equations, because it tells us if we add up the voltage drops as we go around loops, we can just set those equal to 0. But we need to know the voltage drop across each kind of component. So in particular, we're going to need to know how to calculate voltage drops across resistors, and that's what this second thing tells us. This is called Ohm's law, by the way. So Ohm's law lets us write down the voltage drop across resistors. You can see that we're going to need some variable to represent the current across each of these resistors, because we need to know that to be able to write down the voltage drop. So let's give the current across this resistor a name. Let's call it I1. And the current here, let's call it I2. And the current here, let's call it I3. Now the thing about currents is they can be positive if they flow one direction and negative if they flow the other direction. But which is which direction is positive and which direction is negative, is arbitrary. But you have to decide ahead of time which direction counts as positive and which direction counts as negative. It doesn't really matter which way you choose, as long as you're consistent. So what I'm going to do is, for this left-hand resistor, I'm going to say that positive current counts as downward. And actually, I'm going to do that for all the resistors. Positive current counts as downward. So when we find these currents, if we ever get a negative value for one of these currents, that means that current is actually going up through that resistor instead of down. All right. So just to name the resistors, let's call this one R1, this one R2, and this one R3. Okay, so let's use Kirchhoff's law to write some equations. So it says the sum of a voltage drop around a loop should be 0. So let's start here and go around this loop and see what happens. So the first thing we encounter is this resistor. So the voltage drop here is, right, Ohm's law says it's the current times the resistance. So I1 times R1. Okay, and then there's no resistors here, so no voltage drop along this wire. The next thing we hit is this middle resistor, but we're going backwards, right? We're going backwards across this, backwards compared to the direction of positive current flow, so we need a minus sign. So minus I to R2. And now as we go this way, we're going from the negative side of this voltage source, this battery, to the positive side. So that's a negative voltage drop because it's actually an increase in voltage. So we need a minus 4. Okay, and that is all equal to 0. Okay. Now going around the right-hand loop here, we get, let's see. So let's start in this upper left-hand corner. We're going to go down past I2, so I2, R2, and then backwards through R3, so minus I3, R3, and then backwards through this voltage source, so minus 5 equals 0. And now it looks like we're in trouble because we actually have 3 variables and only 2 equations. Usually when you have more variables than equations, you aren't going to get a unique solution. And in this situation, we expect a unique solution because if you built this circuit and turned it on, it would do something, right? It would actually have a certain behavior, and that means that there should be a unique solution to this system of equations, and that unique solution should correspond to the behavior of the circuit if you actually built it. So we're missing an equation, right? That's what I'm trying to say. Since we have 3 variables, we ought to come up with 3 equations somehow. So where are we going to get a third equation from? There's actually one more fact about circuits that I neglected to mention earlier, which is any place where you have 3 currents coming together, these currents have to all add up to 0. And that's just reflecting the fact that as electrons flow through a circuit, you don't create electrons. The electrons move around, but no new electrons appear and no old electrons disappear, as long as you don't have sparks jumping in or out of your circuit, I guess. So we need to write an equation that for this node down here, for this intersection of the 3 wires, so at intersections, all the currents have to add up to 0. So currents flowing in minus currents flowing out have to add up to 0. Okay. Well, at this bottom node, you can see all of these 3 currents are flowing in. So if we add them all together, we should get 0. So I1 plus I2 plus I3 equals 0. Okay. All right, so here's our system of equations. Now we just need to solve this thing. The first thing that we should do, though, is move our constant terms to the other side. And also, remember all these resistance values. We have actual values for these resistances up here, so we should actually put those in. I'm going to actually take this equation that we wrote down last and put it first. So we get I1 plus I2 plus I3 equals 0. And then for the second equation, R1 is 16, so we get 16I1 minus R2 is 8, I think. Yes. 8I2 equals 5 when we move this over. And then the last equation, which is the second one, is 8i2 minus R3 was 4. So 4i3 equals, oh, this is the one that's 5. The one above it here should be 4, not 5. Okay, so here's our system of equations. Now we just need to do what we usually do to solve. So we can subtract 16 times the first row from the second row. We get I1 plus I2 plus I3 equals 0. And then 16I1 minus 16I1, that's no I1s. Minus 8I2 minus 16I2, that's minus 24I2. And then no I3s, minus 16I3, that's minus 16I3. And then equals 4. Okay, and then last equation is 8I2 minus 4I3 equals 5. All right, now just to sort of not have to deal with so many fractions, I'm actually going to, rather than using the second equation to eliminate the I2 in the third equation, I'm going to do it the other way around. So let's take, looks like 3 times the third equation and add it to the second equation. So I1 plus I2 plus I3 equals 0. The third equation I'm leaving alone, so 8I2 minus 4I3 equals 5. And then for the second equation, I'm doing 3 times the third equation plus the second equation. So we get no I2s, and then 3 times negative 4 is negative 12, minus another 16 is minus 28. I3 equals, let's see, 15 plus 4, 19. Okay. All right, now you can see if we just reversed these two equations, we'd have our stair-step pattern to our variables, so we're ready to do back substitution. So this second equation tells us that I3 is minus 19 over 28, which is an unfortunately messy value. It makes me wonder if I made an arithmetic mistake somewhere. Now we can plug that into the second equation. So 8I2 minus, well, yeah, let's just move this 4I3 to the other side. So 8I2 equals 5 plus 4 times I3, which is minus 19 over 28. So that's 5 plus, sorry, minus 40, 76. Oh, I needn't have done that. Let me get rid of a factor of, actually, let me just do that. There. 19 over 7. Right, simplify before you multiply. And 5 is 35 over 7. So 35 minus 19 is 18. Sorry, 37 minus 19 is 18. So 18 over 7. Okay, now we have to divide by 8. So I2 is, let's see, get rid of a factor of 2. So 9 over 28. Okay, and then I1 is, right, this first equation says I1 is just minus I2 minus I3. So minus I2 minus 9 over 28 minus I3. I3 is minus 19 over 28. So we get 10 over 28, which is 5 over 14. Okay, so our currents, I1, I2, I3, are 5 over 14. And this is going to come out into a unit of amps, but that's not important. 9 over 28 and negative 19 over 28. Okay, so it turns out that actually one of these currents did come out to be negative, right? This one did, so that means that the current going through resistor 3, this one on the right, isn't going down, it's actually flowing up, right? So there's current flowing down here, there's current flowing down here, but current is flowing up through that resistor.